So folks, on the last page we looked at some of the motion applications of the derivative, and to do that we had to get the terminology of velocity versus speed, as well as distance versus displacement. Now we're setting ourselves up to look at some of the some other applications of the derivative, and specifically we want to look at something in economics called marginal cost. So economists say that the marginal cost at a certain level of production is the cost of producing the next good. So that's the term marginal cost. So let's say, for example, it costs $1,565 to produce 112 coffee pots, and then if we ramp up production from producing 112 to producing 113 coffee pots, it's then going to cost us $1,572 to produce that many coffee pots. So then the marginal cost of the 112th coffee pot is $7, because that's the difference in the cost at 112 versus the cost at 113. So be careful with this. The marginal cost of the nth good, and this is a numbering issue, the marginal cost of the nth good is the difference between the cost when we produce n plus 1 goods and the cost when we produce n goods. So let's look at this example where the numbers are a little bit easier to work with. It costs $1,000 to make one laptop, $1,900 to make two laptops, $2,700 for three, and $3,400 to make four laptops. So what is the cost of the first laptop? Now careful here. Here I'm just simply asking you for cost, not marginal cost, as I am in the next question. So the cost of the first laptop was given to us as just $1,000. When I ask the question, what's the marginal cost of the first laptop, I'm going to take the cost of the second, or cost of making two, or cost at two, and subtract from that the cost at a production level of 1. So how much does it cost to make two laptops? It costs $1,900 to make two laptops, and only $1,000. It was $1,000 to make one, and so that gives us a difference of $900. That is the marginal cost of what laptop? So pause the video, answer the question. The marginal cost of what laptop? What was the marginal cost of the first laptop? Okay. So what I'd like you to do is go ahead and answer these remaining questions. For this, I'm going to let you do this, the rest of part 2 on your own. Okay, and then go ahead and answer question 3 and question 4. So I'm going to let you do all these on your own and work through them. We'll talk about them in class tomorrow, but I want you to go, I think you've got all the tools you need to work through the remainder of these problems. Okay. And go ahead and finish out page 3 as well. And then go ahead and try number 8. Number 8 is an interesting question in which we look at the length of daylight here in Denver, Colorado. So I came up with this equation from some data that I found on daylight hours. And so we can ask questions like, well, if the length of daylight is given by the time of the year in days, we could ask the question, how long is the day on March 1st? And all we need to do to calculate that is we'd go ahead and plug 60 into this function. So we've got 12.18 hours plus 2.37 times the sine of 2 pi over 365 times, in this case we do 60 minus 80, and this would give us the number of daylight hours. So I'll let you compute that, and that gives us the number of daylight hours at March 1st. And I think I wrote this last year. We're actually at March 6th. If you wanted to, you could figure out what the daylight is for March 6th. Okay. So go ahead and answer each one of these questions. We're going to need these bits of information for class tomorrow, so go ahead and just compute each one of these. Just use a calculator for them. And then I want you to go ahead and find and interpret not L of 60, but L prime of 60. And I want you to give an interpretation for that, and do go ahead and compute that for each one of these. So we'll need that information for tomorrow. Folks, I have one more thing I want to add, and that's what we were looking at, the length of daylight hours in Denver, Colorado, that were modeled by this function here. And I just want to show you the sine function shows up here, and that may be a surprise to some of you, I'm not sure. Here I've got a website that shows where there is currently darkness and where there's currently light on Earth. Actually, that's not right now. Let's change it to right now. But anyway, you can see, and it's a little bit hard to see here, if you're looking at where it's light versus dark, and I'm trying to trace this with my cursor, you can see this shape here, and that shape actually gets a little bit more accentuated around the December and June solstice. But you see that this shape here actually is a sine wave shape, and that's not a coincidence. You can model the daylight hours with the sine wave pretty well. So that's the last thing I wanted to show you. So that's all I've got for this video. You are doing a handful of these exercises on your own, but I think you'll be just fine. If you have any questions, let me know.